Good morning, everyone. We'll start with today's class. Okay, I hope the PPT is visible. Fine. So, till the previous class, what we were discussing about was the stereopsis, that is given two stereo images, the left image and right image. How do you try to reconstruct a 3D point? Okay, that is a point on a 3D object or a 3D scene, right? And we saw the basic concepts of epipolar geometry. So what we discussed was in stereopsis, what we require or what we, the prior information that we assume that we know is the camera parameters. We assume that we know the camera parameters, and with that we try to find out we find out the correspondence between points and then try to reconstruct the particular 3D point, right? So knowing the camera constraints and using epipolar constraint, what we do is first we try to find out the correspondence between 2 points. That is, let's say you have a 3D point, okay, which is given by capital P, and then you have a left image here, and let's say you have a right image here. Okay, so corresponding to this 3D point, I have a particular point here which is given by small p, let's say, and I have another point which is given by small p dash. Okay, so in that case I can say this p and p dash, these are the correspondence point pairs. Okay, that means this point small p and this point small p dash both represent the same 3D point which is capital P, right? So what we do here is, in order, the aim, what we are trying to do is trying to find out what are the coordinates of this, capital point P over here, given these two images. So we have these two stereo images, and you want to reconstruct the 3D scene. What that means is you have to find out what is the coordinates of the 3D point here, right? And for that, what we do is we try to find out what is the correspondence that is given. Let's say a particular point P in the left image. I want to find out what is the correspondent point in the right image, which is given by P dash, so that I can find out this capital P here, right? Now that method, wherein you try to find out the correspondence between the different points, is what you call as binocular fusion, right? Then binocular fusion, it finds the correspondence using different attributes of the images. We'll see what are the different methods later. Okay. Now, once you have this correspondence, then what you do is we try to, compute this 3D point. Okay. And that method, that is called as the binocular reconstruction. Okay. So what we have is we start off with with the prior knowledge of the camera parameters, or we try to calculate the camera parameters. Once that is known, we make use of the epipolar constraint, and we try to find out the binocular fusion or the correspondence between pixel pairs. And once we have the correspondence points, I can finally reconstruct the 3D point. Okay, so here this is a case of only one 3D point. Like that, likewise, like if you're considering a 3D scene or a 3D object, there would be multiple 3D points, right? For all of those multiple 3D points, correspondingly, you will have some pixel pair combinations in both images. Okay, so now what we'll do is we'll first discuss some techniques wherein we do binocular reconstruction. That is, given the correspondences, how we can calculate this point P over here. And after that, we will discuss about binocular fusion. Okay, that is how to find the correspondence and what are the different methods to find the correspondence. Okay, so for reconstruction, what we saw is we have already discussed in the previous class that using the pinhole camera projection model, right? I can try to, I can say, okay, if I have the camera center or the optical center somewhere over here, which is given by O, or in some other notations, it's usually given as C, O or C, right? So given this camera center and the point P, if I project this, I can say that capital P would lie somewhere along this line, right? That means my 3D point would lie somewhere along this line. But using one single image, I cannot say where exactly it is. I cannot calculate this distance, right? So if I have another image over here, and if I know what is the corresponding point here, that is the small p dash, then again I can use, okay, so given the camera parameters, that is given the prior information of camera parameters, which means that, okay, I know what is O dash in this case, the camera center, then I can again use it to project or similar to the previous case, I can use the camera projection model and then say, okay, when I project it like this, right, this point of intersection is my 3D point. So I need at least two images over here, right? And by projecting this line over here, the point of intersection would give me the coordinates of the 3D point. Okay, so this is something that we've already discussed in the previous class, and that is how we try to reconstruct. So point by point we try to reconstruct. So this would give me one point on the object. Now considering another point, I can again repeat the same thing, right? So for all this, what is required is that you know what are these optical centers or the camera parameters, and another one is you need to know what are the corresponding point pairs, right? Only then you'll be able to project and find this. So this is the basic concept of the binocular reconstruction. Now, sometimes, okay, due to let's say there may be some errors due to calibration, or there may be some errors due to finding the exact corresponding pairs between the two objects. So because of some errors that may creep in during the calculation, what happens is when you're trying to project these lines, okay, it may not meet, the lines may not intersect. Okay, so what we've seen or what we have discussed earlier is that you project these lines and the point of intersection would give us the 3D point capital P, right? But because of some errors, there are chances that even if there are some slight errors, the lines may not intersect. Okay, because here we are considering a 3D space, right? If it is a 2D space, you can say any two lines will always intersect. But because this is a 3D space, you cannot guarantee that any two lines would intersect. And if the correspondence pairs are not exactly the same, right? Or there is some error in the calculation, what happens is that you may get lines which do not intersect. Okay, so that means for example in this particular figure, you have a line passing like this and you have another line which is actually passing below that. Okay, so they are not exactly intersecting there. Okay, so in such cases, how do we go about, or how do we do this reconstruction? Okay, we'll see that. So how we do that reconstruction is, there are different methods by which you can go about that. So so one method where you can, what you can do is you can try to now since these two lines do not intersect, okay, instead what you can do is you can try to find out what is the minimum distance between these two lines, right? So to calculate the minimum distance, what we do is we just try to draw a line which is normal to both the lines over here. Okay, so you have a line which is going through, let's say OR, and the other line which is going through O dash R dash, right? So we try to draw a line which is normal to both the lines, right? Both these two lines, and we try to find out what is the midpoint of this particular shortest distance that we have, right? So this midpoint is then considered to be the 3D point. Okay, so what we are saying is that that may not be the exact 3D point, but since because you have some errors over here, what happens is these two lines are not coinciding, which means that there is some error. So in order to compensate for that, what we do is we assume the 3D point to be the midpoint of the shortest distance between these two lines. Okay, so you will take this as the 3D point and then continue with all the calculations. So this is one way by which you can go about doing the reconstruction, okay, when you have errors in the calculations. Okay, now another approach by which you can do the reconstruction is, we know that so let's say P and P dash are the points, the image point pairs, okay, the correspondence point pairs that we have. Capital P is the 3D point, right? And let us assume this M is basically my projection matrix. M and M dash are the projection matrices, which means if you consider, okay, you have P is basically a point in the image here, right? And this capital P that you have is in the 3D coordinates. So this is a 2D coordinate system, this is the 3D coordinate system, and we know that always when you're capturing the images, basically the transformation that occurs is a projective transformation. So I can say that this small capital P that you have, okay, it is having a projective transformation, or it is projectively a projective transformation has taken place between these 2 points, the image point as well as the 3D point here, right? So taking that concept into consideration, I can say this capital M represents the projective transformation between these 2 points, that is P and capital P. Similarly, M dash is a projection matrix between P dash and capital P. So in that case, I can write P cross MP is equal to 0 and P dash cross M dash P is equal to 0. Okay, and we've already seen that this cross product can be it can also be represented in terms of the skew symmetric matrix. That is, I can write bracket Px, okay, which represents the skew symmetric matrix, right? So these two equations here can be represented in this way, in this skew symmetric matrices form, okay, and you get this particular equation. So here, having known the correspondence pairs and the projection matrices, what you have to calculate is finding the coordinates of the 3D point. So in order to do that, what we do is, now what we have is a system of linear equations which is in the homogeneous coordinates. Homogeneous coordinates because you have it in the projective transformation or the projective space, right? So this one you just go about by calculating the using the least square estimation problem, okay, and you do the calculations in order to find out capital P. But one problem with this particular approach is that you won't be able to exactly visualize how it is, right? It does not have any geometric interpretation in this case. All that you do is you write the equations here and try to calculate the coordinates of P, okay. But in the previous case, what you do is, in the previous case, you're actually just trying to find out the minimum distance between the two different points, and that is easier to visualize too, right? Now, there is yet another approach by which you can try to improve the reconstruction, okay? That is, it is similar to the first approach that we had discussed. In the first approach, what we saw is that, let's say you have these lines projected and they do not intersect with each other, and we saw that we take the shortest distance between the two lines, and then the midpoint of that is taken as the 3D point, right? Now, in this approach, what it does is it takes, or it converts this as a minimization problem. That is, we know that here the lines do not coincide because of some error that has occurred between, during the calculation of these pixel points, right? So what can be done is, you can, try to change the position of this small p as well as p dash slightly. That is, within the neighborhood, you can try to change the position in such a way that you can calculate different, or you can find out different estimates of p over here, right? So what we do is we keep on within a particular small neighborhood, we keep on try to change the position of the pixel point pairs here in such a way that this distance that we get, okay, is minimized, okay, or you can say that such that the estimate of capital P, okay, is as close as possible to the actual 3D point P, okay. And how we calculate that is by using it as a distance measure, okay, wherein we try to minimize this particular distance that occurs between the two lines here, because the lines, these projected lines, also varies according to how we are varying this one, right? Accordingly, this distance over here also reduces. So like that, we can reconstruct it, or we can use an approach for reconstruction by formulating this as a minimization problem. So we have discussed now 3 different methods. The first method is where you just take the projection and find out the midpoint of the shortest distance between the two lines. Another approach, the third approach which we discussed, is that we slightly change the positions of the pixel pairs in such a way that we get the minimum distance. And Another method which we algebraically try to solve is we know that there is a projective transformation between the image points as well as the 3D points, and therefore we write the equations in terms of the projection matrices, okay, and then try to calculate the coordinates of the 3D point P by solving it as a least square estimation problem. Okay, so that's about reconstruction. And in the reconstruction method, what we see is for all the methods, it is important that you know the correspondence, or you calculate the correspondence pixel pairs accurately, right? So because otherwise the errors would creep in, and therefore you will have to go about with different methods by which you can correct those errors that have happened, okay, and find the best possible estimate for the 3D point, right? So what is important, more important, in order to ensure that the reconstruction is proper, is that we need to accurately find out the correspondence between pixel point pairs, okay. So what we'll see next is what are the different methods by which we can calculate this pixel point pairs, okay. So if you look at these two images here, this is the left image and this is the right image, right? And what we see here, these lines over here are basically the epipolar lines, okay? So that means I know that if I have, let's say I'm considering some point over here, okay? And this is the epipolar line, which is, passing through that point, right? So I know that the corresponding pixel pair, okay, to this particular point which I'm considering would lie along this epipolar line over here, L dash, which is present in the second image. So that is, if I have L here, okay, and if this is my point, small point, letter P here, then I know that the corresponding epipolar line that I have is this one, okay, that is my L dash, and here I have my point, okay, this will be my point P dash, which I have to find out, okay. So when I find out P dash, that is finding out the corresponding pair, okay, corresponding pair corresponding to this particular pixel point P. Okay, so what we'll be discussing is how we can find out this P dash, right? So like that, it's not just one point, you might have multiple points, right? So let's say these are the epipolar lines for corresponding to all these multiple pixels that we are considering, okay. So corresponding to that, in the right image also you have the epipolar lines, and we know that given a particular point, instead of searching the whole image, you just need to search along the epipolar line only, right? So what we can do is we can first try to align these images in such a way that the epipolar lines that is present in the images would be parallel to the baseline. Okay, so what is basically baseline? Baseline is, if you remember, when we were discussing about the epipolar constraint, if you have C dash, okay, or in some places it is denoted as O dash also. That is, baseline is basically the line which is joining the optical centers of both the cameras, okay. So if you have this baseline over here, what you can do is you can align these images in such a way that these epipolar lines would lie parallel to this baseline, okay. So when you arrange like that, or when you align the images in that particular way, in such a way that it is parallel, you will get a picture which looks somewhat like this, okay. So here what we see is these epipolar lines here, okay, it is parallel to the baseline, so you can assume that the baseline is, somewhere here like this, which lies parallel to this one, right? Now once you are able to make this alignment, okay, so now the search becomes easier, okay, because if I take the first line over here, let's say I'm again taking the first pixel over here, which is small p, okay. Now my search becomes easier because I know that these two epipolar lines would lie along the same row, right? So I need to search only in this particular row, okay. I need to scan only this particular row in order to find out this point P, okay. And so again, what I can do is, in order to find out where exactly is the correspondence of P, okay, here correspondence means what we are actually doing is we are trying to find out the matching point, right? So we have already discussed earlier, there are some methods by which you can try to find out matching points, okay, or some regions where you can do matching, right? So like that, you can try to implement some method wherein you can calculate this matching point and then you find out this particular point, and that would be P dash. Okay, so once you're able to arrange in this way, the advantage is that we now know that the pixel point pairs lie along the same straight line here. Okay, so let's say you're taking one particular edge point or one particular corner point, then I only need to search within that same row, okay, in the next image for finding out this correspondence pair. And to find out which is the correspondence pair, what I can do is I can make use of some kind of a matching criterion to find out where exactly is the pixel pair. So what kind of matching criteria we can use, that we will discuss in the coming slides. Okay, so right now what you need to remember is that what we are looking at is the similarity between the pixel pair. So here for each and every pixel we try to find out how similar it is with respect to this small p, and the one with the best match is taken as p dash or the correspondence point. Like that we do for all the points of interest that we have in this left image. Correspondingly, you find out the correspondence points in the right image by searching along that particular line. Okay, and once we have these set of corresponding points, we can proceed with the binocular reconstruction in order to get the 3D points. Okay, so this is the illustration of the same thing that was discussed earlier. That is, given a baseline. Okay, so this pi bar and pi bar dash that is given here, this is a hypothetical plane which let's say contains the baseline. Okay, so given a baseline, what we are doing is all these epipolar lines that you have, right? These epipolar lines would be arranged, or it will be aligned in such a way that it would be parallel to the baseline, and then we do the search. Okay, so before we proceed further with explaining how exactly is the matching done or how exactly the similarity is done, we'll just familiarize with a concept or with a term which is known as disparity. Okay, so disparity means that it is defined as x dash minus x. That is, let's say the coordinates of the point P is given by x comma y, and the coordinates of the point P dash is given by x dash comma y dash, right? So in that case, if I just take the difference between the coordinates of the x coordinate, I can, I can name that, or that is denoted as the as a term disparity. So disparity mainly means what is the displacement that has occurred between the two images, that is the left image and the right image. Or I can say how much is the motion that has obtained, okay, within the or between a particular object between the two images. Okay, that is known as disparity. And given disparity, which is given by denoted by this small letter d, and given capital letter b. Okay, capital letter b is basically the baseline or the distance between the optical centers. And let's say P and capital P is a 3D point, and small p is the image point. I can write P is equal to minus capital B by dp. Okay, so that means if I take the ratio of the baseline divided by the disparity, okay, so it will be correlated with that of the normalized image coordinate. Okay, so this one we consider it as a normalized coordinate system. Okay, so I can write z is equal to minus b by d. Okay, z is nothing but p by p, right? So if I just substitute the coordinates, I can write it as capital P, that is a 3D point, is given by it's a ratio of the baseline by the disparity into the image point small p. Okay, so basically what that means is this disparity gives a see, the baseline does not change because you have that value is fixed because you have the camera parameters or the camera positions fixed at both the left and right sides, right? So this disparity gives us an information of how far or how close a particular object is. Okay, so we'll just try to understand that later with the help of some examples in the image. That is, when you're calculating the disparity, what we'll see is that the objects which are closer to the camera focal length, or the which are closer to the camera centers, okay, would have a larger disparity as compared to those objects which are further away. Okay, so because of that property or that particular characteristic, we see that it helps us a lot in finding the depth information of the relative objects. That is a relative depth information between different objects. We'll see some examples of that later. Okay, so we were discussing about finding the best matching correspondence pairs. Okay, so what we discussed was, let's say you have these epipolar lines which are aligned parallel to the baseline. Okay, and we said that okay, if I have a particular point P here, then in the right image I need to find out what is the corresponding point P dash, right? So in order to find that, what I said is, so this is the left image, let's say, and this is the right image, right? So what I said is that the search needs to be found, the search for the correspondence point, okay, should be found only along this same row, okay? And along the same row, what we do is we try to do some kind of a similarity measure to see which is the best matching point, right? So what we can do is, in order to find out this correspondence, we can make use of the, or it is the same as saying that you're trying to find out which are the most correlated pixel pairs, right? So we can compare, or we can find the correlation in different by different methods here, right? And so one method would be to compare the intensity profile in the neighborhood of the potential matches. Okay, that is, what we do is we just calculate a window, right? Or we define a particular window of a particular size, okay, which is centered at the point which we are considering. So let's say we are considering a particular window over here, or a small neighborhood, right? And then along this particular line, again you have, you construct the same size neighborhood, and then we try to find out what is the correlation between these windows. Okay, so this is a window based approach, and you call it as the local method. It is a localized method for binocular fusion. Why we say it's a localized method is because we only consider a small neighborhood along around the pixel of interest to us, and then we since we are doing a search only along small neighborhoods, we can call it as a local method. And as I said earlier, this is a window based method where you can just find a window here. So you have your what you're doing is you're calculating different windows, or you're considering different windows along this particular epipolar line. Okay, and we try to find out which is the window which shows us the maximum correlation or the maximum similarity. And what we see is that this particular window will give us the maximum similarity. And so then what we can say is that okay, so these two are my corresponding point pairs. Okay, so that is how it is finalized, or that's how it is chosen. Those corresponding points are selected. So just to give you an example, so let's say you have this as the left image, right? So in this particular left image, let's say this particular point, this black pixel over here is the center pixel that we are considering, right? So if this is the center pixel, and let's say this corresponding value is V, that is the row is V and the column is U over here, right? Now what we do is, in the right image, okay, we assume that it is along that same pixel, or the correspondence pixel is lying in the same row, okay, but the column would be plus D. Okay, plus d in the sense we know that d is calculated by finding the difference of x dash and x, right? So that means the translation that has occurred. Okay, so you can assume that the transformation that occurred between these two images is basically only a translation operation, right? So because of this translation operation, what happens is that for each and every pixel pairs, you can try to find out what is this translation that has occurred, or what would be the disparity in that case, right? Now, given these two, what you need to remember is that it is lying along the same row. So when we are doing this search, what we do is we do the search along the same row, and then we try to find out what is the corresponding pair. Okay. So here, let's just take this as an example here. Okay. So in this example, let's just try to visualize or find out how exactly you're trying to find the correspondence using the correlation. So as I said, let's say you have a point here. Okay, we consider a small neighborhood or a small window. Okay, in the left image, and what we do is, or what we need is, we need to find out this point here, right? This point is my corresponding point in the right image. Okay, so if you look at these two images, the left and right image, it looks like kind of it is similar, but it is not. Okay, it is a little translated version. Okay, and you'll understand that if you look at this particular edge here, you can see that the window has stopped, and you can kind of see a part of the building pillar over here, but in this case you cannot see that. Okay, so that means these two are not exactly the same images. There is a slight translation operation or a transformation that has happened between these two images. So this is my left image and the right image, and using these two images, what I need is, I need to find out what is the, or I need to reconstruct the 3D scene. Okay, this particular 3D scene of this street. So in order to find out or reconstruct the 3D scene, what I require is, I need to find out what are the correspondence pixel pairs, right? So if the pixel that I'm considering is, let's say here, okay, then in order to find out the corresponding pixel in the right image, what I need to do is, by the method of correlation, what I can do is, I consider a small neighborhood, right, or a small window. Okay, and I do a search along a line. So we know that the scan line, or we know that these epipolar lines is a line parallel to the baseline, right? So that is going to be my scan line. The row remains the same. So corresponding to this row where the pixel is located, along that same row in the right image, I start doing a search. Okay, so when I start doing a search, what I do is, okay, I look for one window here. Okay, and I try to find out how much is the similarity between these two. Okay, then I might go for an overlapping window, or I might go for, okay, so it's an overlapping window. I'm just drawing another window over here. Okay, so maybe the next window may be here. So for each and every windows of the same size, it should be the same size, I can consider along this particular line, and the line or that particular point which gives me the best similarity, okay, that one I will choose. Okay, so what happens is, now let's say I'm considering different windows over here, and there are different ways by which I can try to calculate what is the best matching, or how similar it is. Okay, one such method is by calculating SSD, or the sum of square distance. Okay, so if I take the SSD, or if I calculate the SSD error, what happens is, here for all the other that is, if I'm considering this, if I'm comparing this with all the other windows, what I'll see is that you will have kind of a high error value. Okay, but when it reaches this one, because it is exactly matching with each other, what I see is that the SSD error reduces. Okay, it becomes a minimum. Okay, or if it's a perfect case, it would become zero here, right? So it becomes as low as possible, and then for the remaining windows again, what we see is that the error increases. Okay, so like that, along this scan line, if I calculate the SSD error, what happens is, I might get a graph which looks somewhat like this. So in this graph, what I do is, I try to look for the minima point or the corresponding value which gives me the least disparity, right? And then that would be that corresponding point would give me what is it? It would give me what the correspondence between these points here, this point here and this point here. Okay, so it would give me the one with the least SSD error would give me what is the correspondence space. So like this I can calculate for any other point. I can take any other point, I can draw a line, okay, or a row. Along that same row I can keep on checking different windows and look for that particular window which has the least SSD error, and that will give me the correspondence pairs. Okay, so this is one method by which you can find the correspondence between different pixels in the left image and right image. And this method that we just discussed is called as a local method, because we are making use of windows, or we're considering only the small neighborhood around the points in order to calculate that. Okay, and the error matrix that we have used is the SSD error. Okay, and this is also for the normalized image patch. It is also called as the max correlation or the max cosine. Okay, so now one problem with using the SSD metric, what we have already discussed in one of the previous class, is that what you're basically doing is when you're trying to calculate what is the sum of the square difference, you're making use, or you're considering the exact intensity values of the images, right? So taking these two images, I consider the intensity values over here, and I do a subtraction with respect to those intensity values, right? But what happens is that there may be cases when, let's say, you're trying to capture the image, the intensity may slightly differ. Okay, so there might be some variations in the actual intensity values between the two images, even though it represents the same point. So in that case, if there is an intensity variation, if you're using the SSD error as a metric, what happens is there are chances that it may not show a low value, right? Even though it represents the same point, but because the intensity is slightly different, you see that you will see a SSD error there. Okay, so in order to avoid that, or in order to make it less dependent on the intensity variations, what you can do is you can just go about with image normalization, or you can try to normalize the pixel values. So when you're saying you're trying to normalize the pixel values, what that means is you're trying to ensure that there is not much difference between the intensity variations for the same pixel point. Okay, so for normalizing that, there are different methods that can be used. You can simply take the average of the pixel, or you can find the window magnitude that is considered a particular window. Okay, and within that window you calculate a particular value here. Okay, the root mean square here, or you can take the normalized pixel. Okay, that means you take the pixel value and then just try to normalize that with respect to the values in the windows. Okay, so there are different ways by which you can try to normalize the value of the pixels, but normalizing the value of the pixel values would give us better results for the correlation. Okay, because when you're calculating the SSD, since it is dependent on the intensity variations, if you are able to normalize the pixel intensity values, then what happens is you'll get a better correspondence between different pixel pairs. Okay, so again, here you have the okay, just give me a minute. Okay, so here you have the left image and the right image, and we've already discussed the case where you consider a particular window, okay, and you have corresponding windows over here, and you try to find out what is the matching between the windows, and we try to find out which window shows the best match, right? Now, instead of going about with a window approach where you try to, calculate the SSD, you can also, represent these what windows or these neighborhood as vectors. That means I can recalculate the parameters or the values over here. Okay, I can transform this into a vector, and let's say I'm transforming this into a vector which is denoted by WL, and this particular window I'm just transforming that into another vector which is given by WR. Okay, so here what we are doing is we are trying to represent each window, okay, as a vector. So if you have it as a vector in the m square dimensional vector space, depending upon what is the dimensions, okay. Now once you have the vectors, what you do is, in order to find out what is the correspondence between these two vectors. Now, what we are trying to do is we are trying to see how similar they are, or what is the best match between them, right? So in order to calculate the correspondence, or the how similar they are, or what is the correlation between them, what I can do is, given these two vectors, I can simply calculate what is the angle between these two vectors here, right? So here, if the angle that you have, if it is 0 or if it is close to 0, I can say these two vectors are highly correlated with each other, okay? And if they are far apart, the further apart the correlation reduces, okay? And when let's say when it is 90-degree, what happens is that you can say the correlation is nil, okay? So we can make use of the normalized correlation metric, okay, in order to calculate how much is the correlation between the two vectors, or the two windows basically. So what we're doing is, instead of using the normal SSD method where you take different pixel intensity values and find out the sum of square difference, what I can do is I can represent those windows as a vector. So I'm transforming it as a vector, and I just calculate what is the angle between the two vectors, and the lower the angles or the least angles would give us the best correlation or the best results. Okay, so that is the normalized correlation metric. Another metric that can be used is the normalized SSD. Okay, so in order to calculate the normalized SSD, what I do is, just like the previous case, I kind of find out what is the sum of square difference, but in this case it would be a normalized case. That's all. So these are the two metrics that you can use along with image vectors. Okay, so this is an example of a disparity map. We saw that disparity means it's nothing but the difference between the corresponding pixel pairs, right? And we also discussed that the importance of this disparity map is that those objects which are closer to us, okay, or to the camera. For example, in this particular image, you see that some of these regions that you have would be the closest as compared to these regions over here, right? So what we are ultimately trying to do is we want this depth information, right? So this disparity map would help us to give us an idea of which are the objects which are lying closer to us in the sense to the camera center, as compared to those objects which are lying further away. And this is an example of the disparity map, that is, after considering the left image and right image and calculating the disparity values and then plotting it as an image, what we say is you'll kind of see this distribution where you can kind of make an assumption, or you can try to interpret which are those objects which are lying closer, okay, as compared to those objects which are lying further away. Okay, so those with higher intensity values, white or brighter pixels, would mean that it is lying much closer to us. Okay, and those which are on the darker side, or black pixels, okay, would indicate that the objects corresponding to those locations are located much further away. Okay, so this type of information can be made use of when you're trying to, let's say, do a segmentation, or let's say trying to locate or localize any particular object. or so on. Now here this shows some examples of disparity maps. Okay, so let's say this is the input image that you're giving, and for this input image we can calculate the disparity map. So as I said, you just try to find out what is the difference between the x coordinates in the left image and the right image, right? So when you do that, again the effect of window size. So choosing the window size would give us a different result for the disparity, or it has an impact on the appearance of the disparity maps. So this is an example of an image where when you're choosing a window size of 3, and this is an example when you're choosing a window size of 20. Okay, so here the difference that we see is that when you have a window size of, let's say, 3, that is a smaller window, you'll see that there is more detail. That is, here I can make more interpretation of what exactly is lying the closest to us. Okay, what exactly is lying far away, and I can also these small leaves that I see here. Okay, those also I can get that information. So there is more detail in this case, but there is also a lot of noise that has crept in. Okay, so this is one advantage and disadvantage. The advantage is the more details, and the disadvantage is the noise which is present here, right? Now, if I go for a larger window, let's say a size of 20, what I see is here the noise has reduced considerably, but at the same time, it is smoother in the sense the details are kind of reduced. Reduced in the sense you get a much more smoother kind of information. Okay, but at the same time, you do not have these sharp cut. See, if you look at this particular tree itself, I can see the exact information in this case, right? But I cannot see that here. Okay, I get an overall picture, but it's kind of a smoothened disparity map that I get, okay, when I'm going about with a larger window size. So this is an example of using a window-based matching, okay, using the correlation. So here, this is the disparity map that you get, okay, using the approach that we just discussed right now. And this is the actual image data, okay. So if you make a comparison, now here, these colors, it's basically color coded, okay, in the sense you have the disparity map and then that is just color coded, that's all. Okay, there's no other particular interpretation for the colors. So what you need to remember is that the clusters or one particular color just indicates one particular distance or disparity value, that's it. So if you look at this image, what you'll see is that you are able to retrieve most of the information. Okay, that is, okay, now this lies, all this belongs to a particular object and it lies closer as compared to the objects over here or the lamp that you have here and so on. So this is the ground truth data, okay, which is present. So if you make a comparison, you say that, okay, you are able to retrieve some of the information, but at the same time you also have a lot of noise that is crept in. Okay, it is not exactly good representation or a faithful representation of or equivalent to the ground truth which is given to us. There is a lot of noise which is present over here. Okay, and remember that this particular approach that we discussed is a local based method, in the sense we just consider the small neighborhood around the pixels and then use it for calculating the correlation. So the disadvantage is basically that you're making use of only local information. Now another another concept that you need to make that you need to know is about the foreshortening of oblique surfaces. Okay, that means now if you need good results, okay, when especially when you are dealing with the local based methods, what we see is here you need to ensure that the plane, okay, containing these points over here, the plane should be parallel to that of the baseline. Okay, if the plane is not parallel and if it is oblique, what happens is the corresponding corresponding projected image that we are seeing in the image, right? Corresponding to, let's say, if this is the line L and I have the corresponding image, image edge over here, okay, which is represented by L, and the same thing is represented from this camera, that is the right image, I have it as L dash. If I observe L and L dash, okay, what you see is there is a difference in the length, okay. So it could be length, it could be height, okay, depending upon what is the object that we are considering, right? So here you see that there is definitely a difference in the length, okay. So this difference in length actually happens because the plane is not parallel to that of the baseline and you have an oblique plane, okay. So when you have this oblique plane, when you're going about with local method finding the correspondence, it becomes difficult because it is basically not taking into account what is the what is this information or the overall picture. It is not taking that into account, it is only taking the neighborhood pixels. So it does not it does not look at this difference in the what distance between the two lines here, or the images of the line L and L dash here. Okay, so just an example to show that the local methods of correspondence works well when you do not have any oblique planes, but when you do have oblique planes, we need to go about with globalized methods. Okay, so this is just an example which shows two images over here and trying to do a reconstruction from the two images. Okay. Okay, so another method for local method for binocular fusion is called as the multi-scale edge matching. Okay, now in the previous case, what we saw is a matching with respect to the points. Okay, that means I have a particular point in the left image, and what I do is I do a scan along the same line, and then I try to find out what is the corresponding point in the right image. So here, instead of doing that, we can also go about with an edge matching. So in the case of edge matching, what we do is we try to look for an edge and we try to match the edges, okay. And along with that, you can also do a multi-scale edge matching. Multi-scale means we try to convert the image into different scales, and then we can do an edge matching, and this would help us with finding better correspondence between the two image point pairs. So just to show an example of multi-scale edge matching, let's say this is the left image that you have and this is the right image that you have, right? So for the left image, let's say the edges I'm considering is this red boundary, and in the right image, the boundary that I'm considering is the blue one, right? So when I try to just overlap these two images, I may get an image like this with only the boundaries. If I look at only the boundaries, this would this red would correspond to the left and blue would correspond to the right, okay, and it may look somewhat like this, just as an example. And when we are trying to find out the correspondence point pairs, let's say this is one pair of correspondence points, okay, this is another set of correspondence points, this is another set, and this is another set, okay. So let's say we have calculated that by our traditional means in order to find out the correspondence pairs. Now, once we have that, what we do is in the multi-scale approach, okay, so let's say these are the correspondence pairs that we have, okay. From this, we can actually calculate what is the disparity or the offset, okay, and from that we can kind of once that is calculated, we can actually coincide them together, okay, to look somewhat like this, right? So let's say after that you're trying to reduce the scale. If you're going with a lower scale image, I can make use of this offset or the information regarding the disparity. I can make use of that information in order to find out the correspondence pairs in the lower scale image. Okay, and if I do that, what happens is I get better correspondence points as compared to these. Okay, so this is an example. Let's say when you have taken a lower scale image and you have calculated the correspondence pairs using the traditional methods. Okay, sometimes you see that you do not have a correspondence point. Okay, and sometimes it fails to find out the exact correspondence point. Okay, sometimes it may find out the wrong correspondence points, etc. But if you are able to let's say in a particular given scale, if you are able to find out what is the disparity, okay, that is find out the correspondence points and find out the disparity and use this information in order to do the search in the lower scale image, you'll see that you'll be getting better correspondence. Okay, and when you're again using this information for the yet lower scale, you'll get a better correspondence match. Okay, and like this at a different scale level, you can try to find out the correspondence, and that will help us with actually getting better or stronger correspondences between the two images. Okay, it's because as we discussed earlier, finding the exact correspondence points is very important, because otherwise reconstructing or finding the coordinates of the exact 3D point would again be difficult, right? So we need to reduce the errors which is propagated during the finding correspondence points stage itself. Okay, so that it does not, we need not again go about reducing the error in the later stages. So this is one method by which you can try to considerably reduce the errors in finding the correspondence point pairs, wherein you try to find the correspondence at different scales of the image and then combine these information together to find out the strong correspondence points. Okay, this is just an example of a particular image and using the Laplacian operation in order to find out the the zero cross what to say, the zero crossings. Okay, or what you're trying to do is basically trying to find out this disparity between the images and then trying to reconstruct that. Okay, at different scales, just like the previous case, we're just making use of the Laplacian operation for that. That's all. So the previous method of multi-scale edge matching and window-based correlation pixel point pair matching, all those were local methods, okay, because it made use of only the local information. Okay, now what we have is the global methods for binocular fusion, right? So global methods means instead of just calculating or considering the small neighborhood, we try to look for the whole all the pixels, or the whole information which is present in the whole image in order to do the binocular fusion, or in order to find the correspondence between the different pixel points. So for this, what we do is we incorporate certain constraints, which is called as the ordering constraint or the smoothness constraint among adjacent pixels. We'll see what is that. So in ordering constraints, let's say you have an object, okay, and in the object, the three different points that we are trying to locate is the other points A, B, and C. Okay, and let's say this is the left image that I have, and this is the right image which is there. Okay, and the epipolar lines which are corresponding to the left and the right image. Now, if I look at each of these points, what I see is that, okay, so corresponding to A, if I try to project this, I get it as A here, here I get it as A. If I try to project B, I get B here, I get B here. If I project this, I get C here, I get C here, right? So I have all these different okay, I have all these different images of the different 3D points here, right? Now, what this ordering constraint say is that, let's say I have these points A, B, C, and I get the order A, B, C in the left image. Then the right image also I will have the same ordering, okay? That is A dash, B dash, C dash, right? So what I'm saying is that the order in which the different pixels, the images of the different points come in one particular image would be the same order as the corresponding points in this image. That means if I have A, B, C, then here I should be having A dash, B dash, C dash. I should not be having, let's say, A dash, C dash, B dash. Okay, or the order should not be changing, right? So it should be in the same order as this one. Okay, so that is what you call as the ordering constraint. But what we see is that sometimes, it may look like, sometimes it may look like as if, okay, it need not be, it's not much of an issue because, we'll always get it like this. But that's not always the case. Like sometimes, let's say if you have any small object which lies in front of a larger one, that is, if I'm taking a particular 3D scene, and you cannot just say that there is only one object in that 3D scene. Okay, you might have multiple objects. So let's say I have a smaller object which is present in front of a larger object. Okay, and when I'm trying to reconstruct the 3D scene, the different points which I'm considering, let's say, are A, B, C, which are present in the larger object, and point D, which is present in the smaller object. Okay, so if you have it somewhat like this, and when you're trying to project it onto the epipolar lines, what you get would look somewhat like this. That is, I have a point A, okay, corresponding to A I have here. But when I try to project this A onto the second or the right image, what happens is this gets obstructed with the object which is present over here. So since you have that, what happens is you do not get a correspondence pair over here A dash. Okay, because here you're not able to project it, okay, because of the presence of this object here. Similarly, if you have this particular point B, okay, I have the projection B here, but this can also be projected here. So I have the presence of B and B dash. But if I look at C again, C, you're able to project it here. Okay, here you have this particular object which is in on the way over here, right? So this is what you call as or the concept is called as occlusion. Okay, we'll see that. So what happens is, now if you look at the object or the point D, what happens is D can be projected and you get it this way. So now if you look at the order in which the points are occurring, I see that I have A, B, D. Okay, when I'm looking through this way. But when I'm looking through here, what I see is it is B dash, D dash, B dash, C dash. Okay, that means I do not have the correspondence of the point A is not present here. Okay, then what for C also, I do not have the correspondence of the point C which is present over here, right? And here also the order in which it is occurring, okay, there are occluded pixels or occluded points, and moreover you also see that the order here is also not there, right? So this is called as the ordering constraint, where we assume that for each and every pixel pair you do have an image pair, and it occurs in the same order. But sometimes due to occlusion that may not be the case, and you may not have exact correspondence between the two images. Okay, so what you can do is, in order to ensure that the you're still able to get the correspondence between the two images, okay, or you're still able to find which are the exact correspondence point between two images, you can make use of different advanced algorithms. One such algorithm which we'll be discussing would be relying on dynamic programming. Okay, we'll see how that is how exactly that is done in order to find out which are the exact correspondence points. So what you need to remember here is that due to the presence of certain objects obstructing others, you see that when you're trying to find out the correspondence point pairs, you may not always find for all the points you may not find the correspondence points in the other image. Okay, and vice versa also. Okay, so in such cases, what do we do? So here, let us just consider this particular example. So in this example, what we see is I have this particular image here. Now I'm not considering I'm just considering a few points, okay, and let's say these points are here, right? And the left scan line, this is basically the left image I have, and this is basically the right image that I'm having. So if I try to, let's say, I try to project and I try to find out the corresponding points, okay, I get the two correspondence points there. Then the next one also I'm able to get the correspondence points, okay. If I look at the next one, what I see is I have an object over here, okay, and it is kind of, you know, a little, what I say, it is a little front in front of the other point, okay, and because of which what happens is, now let's say if this is the object that we are considering, right, here you see that there's an obstruction and you're not able to exactly you know, project it onto the right image. So that means I get a point over here in the left image, but that point is not present in the right image. Similarly, when I go to the next one, okay, I'm able to project it and I get correspondence pairs. When I go for the next one, again, I'm able to project it over here, okay, I get the correspondence point, but I'm not able to get it here. So here what can be done is, okay, so what we see now is, here I have this information which I have in the left image and I have this information in the right image. So if you try to find out what exactly are the corresponding, so there are four pixel points here, there are 4 pixel points here, but we know that, okay, not all pixel points or not all are the exact matches of each other, right? So in the first case, yes, these two are the exact matches, okay, for both, that is true. And for the second case also that is true. But for the third case, we know that, okay, this does not match with this. This is actually an occlusion, because if you try to trace back, what we'll see is, yes, you get a projection of this one on the left image, but you do not get it on the right image. So therefore, this pixel point that I have is basically an occlusion, okay, or it's an occluded pixel. Now, if I go for the next one, okay, yes, I'm able to find a match. But again, the last one over here, okay, this is also an occluded pixel, okay, and you call it as disocclusion. Basically, for the left image, when I have the occluded pixels, I can call it as occlusion. On the right image, when you have, I call it as a disocclusion, right? So now what the dynamic programming does is, the dynamic programming tries to find out what are these matches, okay, or which are the pixel points which are exactly matching, and it will be able to discard the occluded pixels and the disoccluded pixels, okay, and we'll see how that is done. So as I said, you have the left scan line, okay, and the occluded pixels here. For the right scan line, the same pixels, it's called as the disoccluded pixels. So what we do is, you know, we try to kind of create, for the dynamic programming, we try to kind of create a path, okay, between a path, okay, which is or whose path is decided depending upon what are the pixel pair combinations, and we try to find out what is the you know, most optimal path which is present between the two images, and that optimal path will give us all the occluded pixels, occluded as well as disoccluded pixels. Now what that means is, what we do is, given these you know, scan line along the left image and given the scan line along the right image, we try to create a 2D matrix over here, right, having the same number of rows and columns. Now, starting from this point, what we do is we compare the two pixel pair combinations, okay? And if these are the exact match, what happens is, here we create a path which is diagonal, okay? So each time it gives the exact match, it keeps on going diagonally. But let's say you have an occluded, you come across an occluded pixel, okay? So when it's an occluded pixel, it's not the exact match over here. So what happens is, accordingly, it either goes, okay, vertically down, or it goes horizontally straight, okay? So it either goes down or straight depending upon whether it's an occluded pixel or a disoccluded pixel that you came across, okay? And then for whichever matching pixel pairs that you have, it will keep going diagonal. So Like that we can calculate different paths. Okay, so the path which gives us the least distance, or let's say the least penalty, that means depending upon that is, if it is going diagonal, we do not give a particular penalty, but if it is a horizontal or vertical, we give a particular penalty. And therefore finally, after finding, let's say if you have multiple paths, or if the dynamic programming has identified multiple paths, you go for the path which gives you the least penalty. Okay, we'll see that. So what is done is, right now, let's say this is the start position over here, and I'm trying to calculate what is the match between these left scan line and corresponding right scan line. So what I say is, okay, let's say these two pixels match, these 2 points match, so I'm going diagonally because it is a perfect match. And then now here I came across the occluded pixel. So when I came across the occluded pixel, what I'm doing is, okay, since it is not a perfect match and it is an occluded pixel in the left scan, I go straight, okay, straight this pixel point as well as this pixel point. Again, when I try over here from this point, when I try to calculate, okay, so what I'm doing is I'm comparing with this one now. So this one is already gone, this is gone, right? So these two pixel pairs have already been compared. Okay, that's how you got this. After that, when you try to compare this and this, okay, you see that there is no match there, so this is an occluded pixel. Okay, so that has been considered here. Again, this one, when you're comparing this and this, it is again an occluded pixel, so that is also considered, and you reached here. Now once you reach here, what you do is you compare this and this. Okay, so when you're comparing this and this, okay, you see that it's a perfect match, right? So it will be a perfect match along three such rows, right? So correspondingly, what happens is you'll be drawing diagonal, or the dynamic programming will give a diagonal value, okay, or the path would be diagonal for the next three cases till here. Now in this case, what happens is, if when I'm comparing this, so three cases means now this has gone, this has gone, this has gone. Now in this particular case, what happens is when you are comparing this and this, you see that it is not a perfect match. Okay, so that means this is a disoccluded case. So if it is a disoccluded case, it goes vertical here. Okay, because it's a disoccluded case, and like that we keep on continuing, and we see that, sorry, and then we see that here, like till the end, this would just continue here. Okay, you have it till here, right? So what we what the dynamic programming does is, it is basically trying to get rid of the occluded and the disoccluded pixels, right? And for that, what it does is it will create a 2D matrix having the same elements as that of the left and right scan lines. And along this 2D matrix, it tries to calculate the path here, right? So when trying to calculate the path, okay, it will give a diagonal, or it will go diagonal where you have these perfect matches, and in the occluded cases it goes horizontal, in the disoccluded cases it goes vertical. And this is how the dynamic programming estimates the path. Now once you have the path, what happens is, now it's not just one path. Dynamic programming may sometimes give you multiple paths. So if there are multiple paths, what happens is the path which gives you the optimal value, or the optimal path, is chosen as the the actual path. Okay, and how you find the optimal path is by giving some penalty. Okay, or giving some, what I say, certain values, okay, or certain points, in such a way that you can calculate which one gives the least point possible. Okay, so this is again another example. Okay, so in this example here, whatever you have it as B cross, okay, is basically the occluded pixel. So this is occluded pixel, this one here is also disoccluded pixel, these two. Okay, and the remaining ones are the correspondences for which has been calculated. So here, when the dynamic programming is trying to program it, what we see is, for what we see is, now for the first two cases, that is B, 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 there's a match. So it goes like this. Then this is an occluded case, so you have it horizontal. Then the rest cases, it is R. So 3 hours and 3 hours, which is best matches, so it goes here. Again here this is disoccluded, so it goes down, and so on. Okay, just like how we have discussed previously, right? So what we see is that in the diagonal, as you go diagonal, there is a correspondence, right? And in the other two cases, it basically represents the occlusion cases. So in order to find out which is the best path, what we do is we give some occlusion penalty. Okay, in the sense we add some points wherever you find an occlusion. Okay, and accordingly you try to calculate how much is the penalty or the points for the different paths, and the optimal path is the one with the least penalty that you're having. Okay, so how it's calculated is, just to give you an example of the previous case, let's say this is one path which it has calculated. Okay, and let's say there is another path which the dynamic programming had calculated due to some cases. Let's say it calculated this as an occlusion and this as an occlusion, and let's say remaining also you have some some paths over here, right? So what happens is, now as long as you have this diagonal, okay, you do not give any penalty over there, right? But whenever it comes across, let's say, a horizontal or a vertical path, okay, you give a particular penalty, and let's say the penalty is 10. In this case, we are just considering an example. Let's say the penalty is 10. So if that is the case, what happens is, now in this particular path, it goes diagonal, you do not have a penalty because it's the best match. Now in the second case, here this is diagonal, okay, so the penalty is 0, but here it has got vertical, so it gets a penalty of 10, right? Now in the next case, again here what happens is, since this is horizontal, this gets a penalty of 10. Okay, here again, since it is vertical, you get a penalty of 10. Okay, and then here, let's say when it's going further, here you have it as 0 and so on. Okay, and here you again have another 10 here, right? But here this has let's say this is still continuing, and you kind of get let's say it goes somewhat like this. Okay, or like this also. Okay, in that case what happens is, here again you'll have a 10. Wherever you have those penalties, okay, this 10 gets added. So what happens is, only the optimal path would give us the least penalty which is possible. Okay, whereas all the other, if there are other multiple paths which have been calculated by the dynamic programming, you'll find that the penalty would be more. So by looking at the path which gives us the least penalty, that would give us the optimal path. Okay, and that is how dynamic programming can be used in order to remove the occluded pixels while trying to find out the correspondence between different pixel point pairs. Okay, and now this is an example of, let's say this is the left image and this is the right image. And after having found out the disparity map between the two, if you're trying to plot it in such a way that given the disparity values, you're just giving a topological, representation, that is assuming the values of the disparities as heights, different heights. Okay, this is just a pictorial representation of how it would look like. Okay, so basically the disparity maps would give us an information of which are the objects that lies closer to the camera as compared to the other ones. Okay, like for example, let's say this is the left image and this is the right image. Okay, so in this case what we say is, this is basically a top view. Okay, and for this particular structure, you see that this is an elevated structure, right? And this is basically the background or the streets which are surrounding this particular structure, right? So if I look at the left image, I see that this elevated structure would be lying closer to my camera as compared to the other streets or roads which is lying outside this. Similarly, here also in the right image, I have this particular structure, okay, which is actually lying closer to the camera as compared to the other ones, right? So when I calculate the disparity map over here, similar, I get a similar information where this particular structure lies closer to the camera, okay, as compared to that is the distance. When I'm looking at the distance over here, since it is closer, you find that it has more disparity as compared to the objects which are lying surrounding this. So what the disparity maps give is an information of how close the objects are, and it gives us a relative, distance information. Okay, and another point that we were discussing so far was about finding the correspondence pairs, right? So for finding the correspondence pairs, you can have either you can go about with local methods or you can go with global methods. In local methods, what you do is you just consider for a particular point. If you, let's say you're considering a particular point on the left image, okay. Sorry, let's say you're considering a particular point on the left image, let's say this particular point. What I do is, okay, along that same row, that is assuming that these epipolar lines are parallel to the baseline, then that means the corresponding point pair would lie along the same line or row in the right image also, right? And then along that right image, I can consider a small neighborhood and then try to do a basic matching or correlation between the different windows, okay, along that particular scan line. And you can use various metrics for that. One common metric that you can use is the SSD. So you can use the SSD error in order to calculate which is the best matching point pair along that particular line, and that will give us the corresponding point pairs. And another method is now, because this finding the correlation, okay, or the SSD error, because it is dependent on the illumination variations, you can kind of normalize the pixel intensities before you go about finding these errors, okay. Then instead of going with points, you can also do an edge matching at various levels, that is multi-scale edge matching can be done, okay, wherein you take the information regarding the edge matching or the disparity value that you obtained at a higher level and use that for a lower level, lower level in the sense lower scale, that is lower scale image, okay, in order to calculate or in order to find out the correspondence, and that would give us better correspondence because you're making or you're using a prior information from a larger scale in order to obtain the correspondence in the smaller scale, and that would give us better results, and that is basically the multi-scale edge matching method. And these two methods are local methods. Apart from that, you can also go about with global methods, which we just saw now, okay, where in the global methods you consider all the points which are present along an object. And when we go about the global methods, there are cases of occlusion. So you might get occluded pixels in the left image and disoccluded pixels in the right image. So in order to obtain or in order to find out the occluded and disoccluded pixels and remove them, you can make use of the dynamic programming, and we just discussed the how exactly dynamic programming is done right now. Okay, so with that we'll end today's lecture class. And so today you won't be having a quiz, okay. So today's quiz, I will be that is the quiz questions related with today's topic. I'll be conducting that along with the next class, that is Tuesday's class, okay. So on Tuesday you will be having a quiz with 4 questions, where 2 questions would be from today's topics and 2 questions from the topics that would be taught on Tuesday. Okay, if you have any doubts, you can ask me now.